Good morning, afternoon, or evening to folks tuning in from around the world. As is tradition, why don't you let us know where you're tuning in from? Welcome to the 169th episode of the Qiskit Quantum Seminar. And just a reminder that this seminar takes place every Friday at noon Eastern Time and will be hosted on this Qiskit YouTube channel. You can always subscribe to go back and catch up on anything you missed, but you can only ask questions here, live now, during the seminar. I'm Derek Wong, a research scientist at IBM Quantum, and I'll be your host today. And of course, there's a lot of care and effort that goes into these seminars, so I'd also like to thank video producer Paul Searle, managing producer Olivia Lanes, our producer and host Slako Manev, and co-hosts Ed Chen, Katie McCormick, and Nick Brunn. Today, we'll be hearing a talk by Mark Saffman, who will speak about quantum computing and networking with alkali atom qubit arrays. Mark Saffman is an experimental physicist working in the areas of atomic physics, quantum and nonlinear optics, and quantum information processing. His research team was the first to demonstrate a quantum CNOT gate for the deterministic entanglement of a pair of neutral atoms. He is currently developing scalable arrays of neutral atoms for quantum computation, communication, and sensing applications. He is notably the Johannes Rydberg Professor at the University of Wisconsin-Madison, Director of the Wisconsin Quantum Institute, and Chief Scientist for Quantum Information at Inflection. Hi, Rajit from India, Paul from Oregon, and Hari Priya from Germany. So take it away, Mark.
Thank you, Derek. Happy to be here. Thank you for the invitation to this prestigious Qiskit Quantum Seminar Series. There's a lot going on these days with neutral atom qubits, and I want to share with you a little bit of an introduction and overview of some of the developments, and I'll also share with you some of our ongoing work. I always feel like when I give a talk, people come and listen, either in person or online. There should be a reward for spending some time with me. And that reward is that you get to see some stuff that's not published and not on the archive yet. I encourage people to interrupt me with questions along the way. I'm happy to make this as interactive as possible. So let me just start out by acknowledging my research group. We have three main lines of activity in my university group these days: working on quantum computing, working on quantum networking, and we also have a atomic optical clock project. I'll mostly talk about quantum computing with Rydberg atoms, and I'll also mention some work towards quantum networking, which also will be part of scaling up the computer towards the end of the talk. And again, feel free to interrupt with questions along the way. So I'll start out with a sort of overview, some introduction, and a sense of where the neutral atom approach is today. I'll talk about some recent work towards fault-tolerant memory and talk a bit about networking. So quantum computing, as I think everyone here knows, there's a handful of approaches that are being very actively developed towards quantum computation and information processing. All of those approaches have a timeline from when the first 2-qubit gate demonstration was done with that technology and when circuits were demonstrated. And here I'm defining circuits as the ability to work with more than 2 qubits and to run a sequence of gate operations and perform digital quantum computing. And it's taken a different amount of time for each of these technologies to go from a first gate demonstration to actually running circuits. Neutral atoms are not so young anymore, but actually the last of these approaches to demonstrate both entangling gates and circuit operations, which happened only fairly recently. So for each of these technologies, the progress has taken some time, but a great deal of progress has indeed been made. And we're currently living in a world where we have systems with gate fidelities that are now better than 3 nines for both trapped ions and superconducting systems. And we're also starting to see qubit counts over 1,000. IBM has announced their superconducting chip with more than 1,000 qubits. And although we haven't run full circuits on neutral atom arrays with more than 1,000 qubits, there is already data on single qubit operations on 1,000 plus neutral atom arrays. And I think we're going to see a lot more progress with these large neutral atom arrays in the coming year or two. So why neutral atoms, given all these different approaches? Well, neutral atoms have some very attractive features and uh, provide an interesting route to solving this central challenge of quantum information processing, which is both isolating the system from the environment to preserve its quantum properties, yet being able to control the system to perform computation. And so we start by encoding qubits in the ground state of ground hyperfine states of a cesium atom. Um, and I like to think of these qubits encoded in these m equals 0 magnetically insensitive states as an SI standard qubit. And I say that because the frequency of this transition is currently the international definition of the unit of time, the second. And these states that we use for qubit encoding are exactly the same atomic states that are used for the cesium microwave atomic clock, which currently establishes the SI standard for time. And so atoms in the ground state are very small, they're electrically neutral, and they have very weak interactions, and they therefore provide a superb quantum memory. Coherence times for qubits encoded in this way routinely reach a couple seconds, and even tens of seconds have been demonstrated in these kinds of systems. That's great for memory, but for computation, we need interactions and entanglement. And on this platform, we enable that by shining laser pulses at these atoms, exciting the atoms up to these Rydberg states, highly excited states, where the electronic wave function becomes delocalized. And when we go from the ground state up to these Rydberg states, we increase the interaction between a pair of atoms by some 12 orders of magnitude. And so we have this ability to coherently turn those interactions on and off, and that provides the basis for implementing fast quantum logic that can entangle qubits on demand. So we have both excellent isolation from the environment, but also the ability to control the system and turn on very strong interactions. So here's the periodic table. All the different elements that I've put color on are elements that have been laser cooled, and in many cases also trapped. There's a great range and an ever-growing number of elements that have been used for laser cooling experiments. A subset of those look most attractive for implementing qubits and quantum computing and simulation, and so that's a subset that are colored here. And even among these, I'd say the primary candidates these days are the heavy alkali atoms, rubidium and cesium, and alkaline earth atoms, strontium and ytterbium, although it sits down here with the lanthanides, it has properties that are essentially very close to that of the strontium atom. When we use neutral atoms for qubits, our challenges lie in a somewhat different space than some of the other modalities. There's really no qubit fabrication needed for neutral atoms. We have these perfect nature-provided qubits. They're all identical, and using standard techniques of laser cooling, we can readily prepare 1 million cold cesium atoms in a magneto-optical trap. The technical challenges, the competitive differentiators lie completely in the ancillary technologies, which includes vacuum cells, lasers, beam steering optics, photonics, control stack, and software. Some of these technologies are common to all approaches to quantum computing, but in particular, the vacuum, laser, and optical technologies are specific to atomic-based approaches and are part of the roadmap that we have both in academia and in industry for developing this technology. And I'll say a few words about some of the challenges and some of the ideas for scaling up this approach and improving the performance. So really these systems start with trapping single atoms so that we have single atomic qubits available for us. This was first done more than 20 years ago in what have come to be called tweezer traps. So one takes a laser beam, focuses it to a small spot, and that focused light which is red detuned from a strong atomic transition, provides an attractive potential. And if one overlays one of these focused laser beams with a cloud of cold atoms created in a magneto-optical trap, one can have single atoms enter and leave this kind of trapping potential. And there's something called a collisional blockade, which prevents more than one atom being in the trap at a time. And so one has 0 or 1 atoms that can, and this kind of trap very effectively provides a basis for trapping atomic qubits. These kinds of traps can also trap Rydberg states of 2-electron alkaline earth atoms. There's another version of this kind of optical trap, which is what we call a blue bottle trap. If we use laser light of a wavelength which is on the blue side of an atomic resonance, that is a shorter wavelength or higher frequency, then the light has a repulsive effect on the atoms. It pushes the atoms away. And so if we create a dark spot surrounded by light in all directions, that's an optical bottle, then we can trap the atom in the dark inside the bottle. This was done a decade or so later compared to the tweezer traps, but can also be used for trapping single atoms that go in and out of the bottle. And these blue traps can also be used to trap single electron alkali Rydberg atoms. The blue traps, the bottle traps, are more complicated in terms of the optical pattern, the optical engineering compared to the tweezer traps. They do have some potential advantages in that the atom is sitting primarily in the dark. It sees less background light, so it's less perturbed and less susceptible to decoherence caused by that trapping light. So those are single traps, and then to build a processor, we want to have an array of traps, and there's a number of different technologies that can be used for preparing arrays of optical traps for atoms, and this can be done in 1D, 2D, or 3D, and I'll just show you some of the approaches that have been used. One can use a microlens array, that is an array of small focusing lens elements to create a 2D grid of these tweezers. And here's an example of that from a group in Darmstadt, the Birkel group. One can use a digital mirror device, the same kind of device that projects PowerPoint presentations up onto a screen. This is some work from a group in Strasbourg using a digital mirror device to create arrays of traps. One can use phase spatial light modulators to implement holograms that implement large arrays of these tweezer traps. This is work out of Dirk Engeland's group and the folks at Harvard using a spatial light modulator, making very large uniform arrays. And here's one example from my own work, which doesn't use an active device, but uses an optical mask, a nanofabricated optical mask, and some ideas from Fourier optics to filter the light transmitted through this mask to also make very large arrays of traps for trapping atoms. So there's different technologies that are in use, and these, as we'll see in a moment, have already been scaled up to more than 10,000 site trap arrays. So when we load atoms into these optical traps, due to the collisional blockade, we generally get half or so of the traps with an atom in them, and half of the traps remain empty. And that's because if we load an even number of atoms into one trap, due to a collision process, pairs of atoms will be ejected. So if we start with an even number of atoms, we'll eject out to 0. And if we start with an odd number, we'll eject out so we have one atom remaining and there's no longer any collisions. One could take advantage of the long-range nature of Rydberg interactions, which I'll get into in a bit, to think about working with a partially populated array that does require a fast runtime compilation of the control pulses. A much more convenient solution has emerged, which is to use atom rearrangement, where one takes a snapshot of the distribution of atoms and then uses optical tweezers to grab the atoms that are present, move them around, and completely fill a subarray as a starting point for doing computation. This was first demonstrated in 2016, and as sometimes happens, really happens simultaneously in a couple different research groups. At the Qiskit lab in Korea, it's the Lucan group in Harvard, and Antoine Broes's group outside Paris all demonstrated these atom rearrangement ideas. This work from Korea used spatial light modulators to rearrange the atoms, and the original work at Harvard used acousto-optics in 1D, and in France, acousto-optics in 2D to create regular patterns of filled subarrays of atoms as a starting point for computation. Also, some other methods have been demonstrated, and this can be done in 1D, 2D, and also iconically also in 3D. So this is a picture from the French group with an Eiffel Tower created out of single atoms in 3D. And I never tire of seeing this picture, which I think is really quite remarkable. So we have techniques now for preparing regular arrays of single atoms. And here's a collage of pictures of experiments going on around the world from a number of different groups, creating arrays in different geometries, arrays with different species of atoms, with different numbers of trapping sites, and also using, in some cases, multiple atoms at one time. Here's a picture from Hannes Bernin's group in Chicago, where they've trapped both rubidium and cesium atoms in an interleaved array, and that's a setting for working with logical qubits. And I'll also mention some of our own work in that same direction. So there's been really rapid progress in scaling up these atom array systems. Here's a chart of the size of the arrays that have been demonstrated over the last couple decades. And so first trapping was done in 01 or so. In 2005, my group had a small array of, I think it was 5 sites. And there's now a number of groups that have exceeded 1,000 qubit barrier. And very recent work from the Endres group at Caltech has a 12,000 site atom array. So really spectacular progress in scaling these up to larger systems. A couple examples from my world, this 1200 site array of bottle traps. So these are these Bluetooth tune traps, and this is an averaged image of the array with cesium atoms in these sites. And here's some work from Inflection, where they've done a 1600 site array, also of cesium atoms using a spatial light modulator. These are now ready-tuned tweezer traps. And we're not doing full computation or running circuits on this, but we have already validated global single qubit gate operations in these arrays, and just shining microwaves at these hyperfine qubits. It's not hard to sort of get right out of the box pretty good fidelity. So this is close to 3/9 of fidelity just in the very first attempt on an array like this. So good progress in scaling these systems up. How far can you go? It's an interesting question. So here's a sort of estimate of what might be possible. Supposing I wanted to build an array to trap 100,000 cesium qubits. You need a certain trap depth to hold on to the atoms. 0.5 millikelvin is a good number. If I have good optics and space these sites by 1.5 microns, and you run the numbers, with this trapping wavelength, you would need about more than 100 watts. That's a lot of power. On the other hand, that's 100,000 atom array in a footprint which is about the size of one transmon qubit. So, an amazing density, I would say, of qubits potentially. That's a lot of optical power. Certainly possible to build a laser with that power level, but we don't really want to be sending that much optical power around. And one can certainly think about optical designs that recycle the light, for example, by putting the atom array inside a resonator. And it's reasonable to assume that one could reduce the power requirements by a factor of 50 or more, which would mean we just need a couple watts. And those kinds of ideas not exactly the design I'm showing here, but those kinds of ideas have already been implemented by a couple groups who have shown that reusing the light in a build-up cavity can be a viable approach to building large arrays with very moderate requirements on the optical power. So I think there's a real path to scaling these things up to very large systems. But then you have to ask the question, how are we going to optically control that large an atom array? The wiring in these atomic systems is not electrical wires, it's optical beams. And so we need systems that can manipulate dynamically optical beam patterns, point laser beams at different atoms, and rapidly modulate them in time and space. And this is one of the technology challenges for this field at this time. There's different approaches, and there are approaches based on available off-the-shelf components. There's something we already implemented using acousto-optic rapid scanning of laser beams. We have proposals for combining acousto-optics with spatial light modulators, which takes advantage of the speed of acousto-optics and the high spatial bandwidth, large number of addressable sites that you have with spatial light modulators, although they're slow. And by combining those technologies, one can perhaps get the best of both worlds. There's also ideas for large high-speed addressing using digital mirror devices. And then there's active work from several groups in looking to the future to integrated photonics. These are not devices that exist at scale today, but these are some of the directions being pursued, arrays of acousto-optic devices, combining spatial light modulators with Mach-Zehnder interferometers in an integrated photonic platform, and also Mach-Zehnder interferometers coupled with waveguide arrays and grating couplers. So these are all approaches that I think will continue to be developed in the next couple of years. So let me turn now to the Rydberg physics and say a few words about how we actually entangle atoms. And I'll just stop for a second there and just ask if there's any questions so far.
I think it's really convenient that you're going to this because one of the main questions so far is what is a 0 and a 1 in these systems? And the question was, does it correspond to the atom being there or not in the trap? But I think you're just about to get to that soon, it seems.
Sure, I went over that pretty fast in one of the early slides. The qubit always corresponds to an atom being in the trap. The vacuum cell is never perfect, so one does lose atoms. And one of the significant challenges with this modality is to replace atoms as they're lost as part of the error correction protocol. And people have started to develop that capability and demonstrate it. But the 0 and 1 are encoded in two different atomic substates, hyperfine Zeeman substates of the ground electronic configuration. So both 0 and 1 have very long lifetimes, coherence times of several seconds, and they do correspond to the atom being present.
Great, thank you. Another question I had was you showed a lot of really interesting pictures of the different arrays and different configurations, 3D and dual species. I was wondering if you could comment very briefly on the applications, in particular the 3D trap and then the dual species one, if you weren't going to get to it later.
Sure, I'll come back to the dual species, so let me leave that for now. So the applications for these arrays are really in a few areas. Digital quantum computing, which is what I'm focused on. They've also been used for beautiful work already on analog quantum simulation, where one uses the Rydberg interactions we're about to talk about between atoms, not just to implement gates, but to implement spin models. For example, Ising Hamiltonians using the analog interaction between Rydberg excited atoms. That in particular is work that's been done at Harvard in the Lucan group and also in the Broes group in France and others, Backer group at Princeton and a number of others now. And the different arrangements just correspond to different ways people are setting this up. These arrays of atoms are also starting to be used as part of sensor devices, so for atomic clocks. and that allows one to combine the quality of atomic transitions for making high-performance clocks with the ability to entangle the atoms to further improve the clock performance. And then this two-species array is specifically intended for error correction applications where one species acts as data and the other species act as ancilla qubits. And then using different species, they can be independently controlled and measured.
Great, thank you. And one final question, and I think we can continue. An audience member asks, regarding the light-induced collisions, do they happen not only in the dipole trap, but also in the optical tweezers?
The dipole trap is the optical tweezer. They also happen in the bottle trap, the blue trap. So as long as these traps are small, and they're typically sort of around 1 micron in size or width, you get these fast collisions between the atoms that do lead to this collisional blockade and single atom occupation.
All right, thank you.
Great. Okay. So Rydberg physics. So what's a Rydberg atom? It's a highly excited state of an atom, but it could also be an ion, a molecule, an exciton, and a solid state host. And these are states of atoms that have exaggerated properties. And for quantum information, the enabling feature of these Rydberg atoms is that they combine exceptionally long lifetimes with exceptionally strong interactions. And that is what is enabling for preparing entanglement with very high fidelity. It's also the case that accessing specific Rydberg states, so the Rydberg states are any of these states up here in this Grotrian diagram of cesium, accessing specific Rydberg states, and in some cases more than one Rydberg state at a time, allows one to tailor the interactions to different tasks, such as engineering the angular and distance dependence of the interactions. And I'd say those opportunities have only been sort of the surface of that has been lightly scratched in an experiment, but there's certainly a lot of theory ideas already developed for how one could use that in interesting ways. And I've just highlighted one particular theory paper here that looked at implementing spin ice and dimer models using engineered Rydberg interactions. For people who want to get into this area, you don't have to start from ground zero anymore. There are now very good open source codes from a couple groups that allow you to calculate all the parameters of interest of interacting Rydberg atoms. And I put a couple references here. So let's look a little bit closer at some of the properties. The size of these Rydberg atoms scales the principal quantum number squared times the Bohr radius, and the lifetime scales as close to the principal quantum number cubed for low angular momentum states. So for example, 100s orbital of a cesium atom in a room temperature environment, that wave function is about 2 microns across, so that's a very big atom, and it has a radiative lifetime in a room temperature environment of something like 300 microseconds. So these are very long-lived excited states. These are low angular momentum states, which can be excited in a very convenient way using 1 or 2 photon laser excitation. Using more sophisticated techniques, one can also populate high angular momentum Rydberg states. So this is an example of what's called a circular state, which for a given principal quantum number, here 100, has the maximum allowed angular momentum and the maximum projection of angular momentum. The wave function for that state is a toroid, and for the 100, sorry, that's not 100s, but it's n equals 100 state of maximum angular momentum, it's got a size of about a micron, and these states have lifetimes that scale as n to the 5th. And so if you go into a cryogenic environment, not a dilution fridge, but a sort of Kelvin scale temperature environment, you can get lifetimes up to a second. So potentially one could reach extremely high fidelity entanglement using these kinds of states, and there's efforts underway in a few groups to do that. These Rydberg excited atoms have very strong interactions. Here's a plot of the interactions strength in frequency units versus the physical separation of a pair of atoms. When in the ground state, the neutral atom interaction is dominated by a magnetostatic dipole-dipole interaction. This is just the interaction of the magnetic moments of the electrons. That's a 1/r cubed, which is sub-hertz at a few micron separation, going up to higher and higher Rydberg levels, and we do that by tuning the excitation lasers appropriately. We get stronger and stronger interactions, which are 1/r cubed at short range and transition over to 1/r to the 6 van der Waals at longer range. And just to put a number there for you, if I go up to the 100S state, I can get about a megahertz of interaction at 20 microns. And so that potentially allows one to interact with quite a large number of atoms directly without moving them around using the long-range nature. So the key phenomenon associated with this Rydberg interaction is what's called Rydberg blockade. So Coulomb blockade is the phenomenon where only a single electron at a time can pass through a very narrow junction due to the Coulomb repulsion between electrons. And with the Rydberg interactions, we have a similar phenomenon. If we have a pair of Rydberg excited atoms, the energy eigenstate for double excitation has a 1/r to the 6 dependence at long range. So there's a molecular energy eigenstate with this van der Waals scaling. And if I excite a single atom here and another Rydberg atom far away, well, that's fine. They have a weak interaction at large distance. I can excite both of them. If I try and excite a second atom closer in with a certain excitation rate omega, well, if I'm too close in, my laser will be detuned from the molecular eigenstate, and I'll have only a partial excitation. And at the distance where the excitation rate equals the Rydberg energy shift, that defines a blockade radius, which scales as a C6 coefficient divided by the excitation rate to the 1/6 power. And if I try and excite a second atom at very close range, it essentially won't be excited because I'm very far detuned. And so that's inside this blockade radius, I can only have one atom excited at a time. And really, this Rydberg blockade is very quantum mechanical. We use the blockade to prepare entanglement, but in fact, two atoms are never excited and in some sense never interact. They interact virtually, and that makes the interaction or the entanglement mechanism very robust, because if I'm inside this blockade distance, it doesn't matter exactly what the atomic separation is. I still have good suppression of the double excitation. So I have a very robust entanglement mechanism and no interatomic forces that could lead to heating of the atoms. So that's the basic mechanism that underlies entanglement protocols for gates. And it's interesting to look at this blockade phenomenon in a couple different limits. So imagine I have an atom that I'm exciting up to a Rydberg level. There's a blockade distance that depends on atomic parameters, a C6 coefficient, and how fast I excite the atom. And suppose I have an array of atoms that I shine laser light at uniformly and try and excite them. Well, there's a limit where the blockade distance is small compared to the physical separation of the atoms. And that limit, I will excite all of the atoms to the Rydberg state. That can be very useful for quantum sensors and for simulation of many-body physics where I have multiple atoms excited. So that's a weak interaction limit. There's an intermediate limit where the blockade distance is comparable to the physical separation of the atoms. In that situation, I can excite some, but not all of the atoms. And which atoms get excited will tend to emerge out of a self-organization type process where the atoms will arrange themselves to minimize the energy in the pairwise interactions. And one of the consequences of that is that spatial patterns, spatial symmetries will naturally emerge, as was seen by the Bloch group in Munich back in 2012. And then there's the limit of very strong interactions where the blockade distance extends over this entire array. And in that limit, only one atom will be Rydberg excited, all of the others will be blockaded, but any of the n atoms could be excited. And if this is a coherent process, what we're preparing is actually a quantum superposition of any one of the n atoms being excited. And that gives us access to W states in a very natural and elegant way, where we simply shine light at the atomic array, and we, in one step, can prepare these W states of n atoms. When one does that, the coupling strength from all atoms in the ground state to this W state scales as the square root of the number of atoms. So one also gets this enhancement of the coupling. And this was also has been demonstrated for preparation of multi-particle entangled states in a very straightforward way. And it's this strong interaction regime that's used for controlled Z and controlled NOT gates for preparing entanglement of individual qubits. And although I love talking about gate protocols and exactly how they work, I decided not to do that in this talk, but rather just give you a sense of what's happened in this field in terms of improving the fidelity of pairwise entanglement using this strong Rydberg blockade mechanism. The first experiments were done in 2010, and there's been, in recent years, very rapid progress in the fidelity of two-qubit entanglement via Rydberg interactions, where the latest results are now approaching 3 nines of fidelity. And I think what's very exciting is that there are now demonstrations of high fidelity entanglement of pairs of Rydberg excited atoms using 4 different atomic species. There's this 0.995 result from Harvard using rubidium atoms. At inflection, we have 0.9935 using cesium atoms. At Caltech from the Endress group, there's 0.996 with strontium. That's now the best result out there. And from Atom Computing and the Thompson group at Princeton, there's 0.994 with ytterbium. So these are all different elements, different wavelengths of excitation. These experiments are 2 photon excitation. These experiments are 1 photon from a metastable state. There's variations in the exact gate protocol being used. And I'd say what's exciting is that really, I think we're nowhere close to the fundamental limit here. And these experiments are currently limited by purely technical aspects, such as laser noise, beam pointing noise, spatial structure of the beams, atom motion. We need to make the atoms even colder. Atom position noise, background electric and magnetic fields, intermediate state scattering for 2 photon excitation. And I believe in the coming couple of years, we're going to see these experiments push beyond 3 nines, which is going to be very exciting. So there's been a lot of progress on the entanglement, and a lot of people have joined this field. So you see not only that there's the points are trending down, but there's a higher density of points. There's many groups now building these experiments, and I think more than 100 new experiments being developed worldwide at this time. So these experiments take place in one of these labs with this crazy amount of lasers and optics and so on. Back here is the core of the experiment, the quantum processing unit. And here's a CAD picture of one of those. There's a vacuum cell at the center of it, where we have the atom arrays trapped, and then there's a lot of optics that allow for preparing the arrays of traps and rearranging atoms and pointing laser beams at different sites, and then high numerical aperture objective lenses for imaging the atoms onto cameras for measurements. So what can we do today with these systems? I want to share some work in progress using the machine at my university lab. So we have an array of cesium atoms. We can perform global single qubit operations by illuminating the array with microwaves that couples the 2 hyperfine states. We can perform single qubit Z rotations by coupling one of the ground states to an intermediate state to provide a phase shift on one of the states that gives us Z rotations. And by combining the optical addressing with microwave pulses, we can perform our theta phi rotations. So this is a rotation through an angle theta about an axis making an angle phi with the x-axis on the equator of the Bloch sphere. We can do that locally using a combination of optical and microwave addressing. And then we perform entangling operations by illuminating pairs of atoms. And sort of typical numbers in my academic lab are 1 qubit gate fidelities between 2.5 nines to 3.5 nines. Our 2 qubit fidelity is about 98%. Measurements are about 99. The gate times here are sort of a couple microseconds for 1 qubit gates, half a microsecond for 2 qubit gates, and coherence times of about a second. So we, a couple years ago, used that system for demonstrating multi-qubit entanglement and algorithms. We demonstrated phase estimation and QA/OA, and we had stationary atoms and did fast steering of the optical beams to implement gates between different pairs of atoms in the small array. There was a parallel work from the Lukin group based on transport and showing that they could transport atoms into an entanglement region, which allowed for many parallel CZ gates by moving the atoms with acousto-optic deflectors. So it's kind of different ways of approaching how to do the control. And we have some work in progress. We try and combine these two ideas, that is, combine optical scanning and atom motion. So we've implemented Rydberg control beams and the gate control beams using shaped beams now, so-called top hat addressing beam, where we have not a Gaussian beam, but a fairly uniform illumination. By putting the atoms close together, we can do a CZ gate with one excitation beam, and by separating the atoms out, we can do single qubit gates on individual sites without interfering with neighboring sites. And we're able to generate these top hat beams with a diffractive element and then rapidly scan them using acousto-optic deflectors. It's not the fastest architecture for NISQ, but I believe will become very powerful when we move to a logical qubit architecture. And so here's an example of implementing this fragment of a VQE circuit by both turning on laser beams in different places and moving the atoms around to enable both 1 qubit and 2 qubit control with the system. So using that, we've been working on implementation of a VQE simulation of the Lipkin-Meshkov-Glick model. So I'll take a few slides and show you some work in progress on that. So this is the LMG Hamiltonian, which was introduced back in the 60s as an exactly solvable model, which was introduced as a way of benchmarking numerical calculations of many-body spin models. And so I find it very appropriate that we're also now using the same model to benchmark quantum calculations or quantum simulations of spin models. So this is one version of the LMG model where V is an interaction parameter. It's exactly solvable, and so we know the structure of also the ground states. And it turns out for n spins, the ground states are states of maximal J. What that implies is that we don't have 2 to the n dimensional state space for n spins, but we only need to represent 2J plus 1 states, all the MJ states corresponding to a particular value of J. And symmetry in this Hamiltonian actually reduces that number to J plus 1. Because if you look at the interaction term, XX and YY, change M by either 0 or plus minus 2, so only half of those states are relevant. So we only need J plus 1 states to simulate the ground states, and therefore we only need order log n qubits to represent n spins. So very efficient encoding is possible when studying the ground states. The trade-off with that efficient encoding is that the number of measurement bases that we need for VQE is increased. But using a gray code approach, we can determine the energy by measuring in just n+1 bases. So, remarkably, this encoding can take us past 100 spins with just 6 qubits. We could do more than 1,000 spins with 9 qubits. Of course, that does not imply any kind of quantum advantage. I can simulate a 10-spin problem, 10-qubit problem on my laptop with no trouble. But I do find it interesting that we can, in principle, or we can indeed simulate very large spin models when we're interested in states that have particular symmetries using a very small number of qubits. And so we've been doing this in the lab. Here's an explicit example for the 7-spin state. So the 7-spin state, ansatz state for the ground state of this Hamiltonian has j = 7/2. And there are components of the solution with m -7/2, -3/2, 1/2, and 5/2. So that's 4 states. So I can represent that with 2 qubits. And there are 3 variational parameters. So that's the ansatz for the ground state written out in a JM basis. I could express that in terms of the spin basis, which is much more complicated, but that's what those states would correspond to in the spin basis. And so we've been implementing that on this machine where we're both moving the optical beams and moving the atoms. Here's a raster scan for this 5-spin case that has 2 variational parameters. So we scanned across those 2 parameters and have good correspondence between experiment and theory. And then we sat at the minimum found from the scan and performed zero noise extrapolation in the way that was introduced by the group at IBM a few years ago. So where we added noise by increasing the number of CZ gates, since that's our primary contribution to noise, and then we can extrapolate back to 0. And we find that we agree with the exact ground state energy to a couple percent from the zero noise extrapolation. So that's a 5-spin case. We've looked at 7 spins, in which case there's now 3 variational parameters. That's more than we want to scan over, so we closed the loop and implemented an Elder-Mead optimizer. Here's the evolution of the 3 variational parameters. Here's the evolution of the energy, and this converged after about 30 iterations. And then we again performed a zero noise extrapolation, extrapolating back to 0 noise, and we get very good agreement with the exactly calculated ground state. So I will admit these are actually, because of the way we do the encoding, these are 1 CZ gate circuits. So not very challenging. We do want to go beyond that. We're currently running a 15-spin case, which will be more CZ gates, and that's in progress right now in the lab, and then we hope to get this submitted. So that's one example of something we can do with these Rydberg atom systems. And let me now turn to a couple things in progress, looking towards the future to logical quantum computation. So the future is certainly going to be fault tolerance.
Oh, sorry, Mark. Maybe we can take a quick pause here and then answer questions that have come up in the meantime. One question asked is, in the strong Rydberg interaction regime, can you deterministically excite a particular atom without individual addressing?
Well, if you don't have individual addressing, you cannot excite just one atom, but we implement individual addressing. And there's different ways it can be done, but the most direct way is that we focus the laser beam to a small spot so that if we have 2 focused laser beams, they interact with 2 selected atoms to perform a gate between that pair. The surrounding atoms that stay in the ground state don't see that Rydberg interaction, or they see it extremely weakly, and so we're able to select just a pair of atoms.
Great. And then another question, is there a reason why it seems heavy alkali atoms form better qubits?
Yeah, one has a whole range of alkali atoms, but it turns out that the lighter alkalis have relatively small hyperfine splittings in the excited state. And that makes the sort of preparation operations and measurement operations that we need to prepare an initial state and to measure the states, that makes it difficult to perform those operations with high fidelity. And that's why the heavy alkalis are preferred.
Okay, thank you. Here's a more technical question that I don't quite understand, so maybe you can make some more headway into it than I can. In Rydberg atoms, you can define a qubit in an excited doublet, ns, n prime p. On the other hand, in some atoms, you may also define a qubit in a ground nuclear spin doublet. The question is, in cases where you have both doublets in the same atom, is there a scheme that allows transfer of the qubit state between the two doublets?
There is, because we can move around in the state space provided by the atomic levels sort of at will using optical pulses and also microwave pulses in some cases. So you can define a qubit in the ground hyperfine doublet, and that's a very long-lived qubit. You can also encode a qubit in one ground and one Rydberg level, and that's done in some of the quantum simulation work. You can also define a qubit in two different Rydberg levels. That's also done in some of the quantum simulation work. However, when you use one of the Rydberg states, not just for an entangling gate, but you use a Rydberg state to define the qubit, then you don't have seconds of coherence time. You have hundreds of microseconds of coherence time. So you're in a different regime as far as performing long calculations. And that's one of the limitations of the analog simulation approach.
Got it. Thank you. I think that's it for now.
Okay, great. I may be a little behind, but let me press ahead. So, error correction, fault tolerance is what we need to unlock the full promise of quantum computing. And maybe you might think of an entry-level quantum chemistry application as 100 logical qubits and 1 million operations. Undoubtedly, we're going to need much more than that, but let's start at not too ambitious a point. If I use surface code and I have 3 nines of fidelity, those 100 logical qubits are going to be something like 40,000 physical qubits. And here I've just tried to give a sense in an approximate way of how many physical qubits per logical qubit and how many logical operations we can perform for different assumptions about gate fidelity. And at 3 nines of fidelity, we're talking about 40,000 physical qubits. How do we do better? Either we push in this direction and get the fidelity much higher, and can we get past 4 nines of fidelity? Time will tell, but it seems very challenging. Or can we make more efficient codes? And that seems perhaps an easier near-term approach than pushing the fidelity well beyond 4 nines. And surface code is the current leader in terms of implementing error correction. And if I look at the surface code, an NKD code, there's a code rate, number of encoded logical qubits divided by the number of physical qubits. And one can define a figure of merit for these codes as kd squared over n. So number of logical qubits, code distance squared divided by number of physical qubits. And the surface code asymptotically is limited to f equals 1/2. And so at large code distance, which is what we want to efficiently suppress errors, the encoding rate goes to 0. And we know from the BPT bound, Ravi Pulin Terhal, that any code in 2D with geometrically local check operations has f going to a constant. And so we really cannot do better than the surface code if we limit ourselves to geometrical locality in 2D. And that has led to, I'd say, an explosion of activity in codes that go beyond this geometrical locality and seek to improve on these bounds. And so one example is this work from the folks at IBM, very interesting work on this bivariate bicycle code on a torus, which breaks the constraint of geometric locality and thereby provides much more efficient scaling and higher performance from the error correcting code. So this bicycle code is a weight 6 code. Each check qubit, each ancilla connects to 6 data qubits. 4 of them are nearest neighbors. 2 of them are long-range interactions. but the code lives on a torus. And so a nearest neighbor interaction from, say, this check qubit would go all the way over here. If you're able to do that, you can have a much higher figure of merit, about a factor of 20 better than the surface code. But how do we implement those long-range interactions? So the IBM paper that came out recently alludes to some ideas for how to do that with superconducting wires. There's been related work on a hypergraph code where non-locality is provided by atom transport. This is the Harvard group and Chicago. And also Fred Chong's group in Chicago has looked at atom transport for the bicycle code. We asked ourselves the question, could we implement this in place? Could we perform the check operations for syndrome measurements in place without atom motion as a way of making the implementation faster on the neutral atom platform? And we have a proposal for how to do that in this preprint, and there's two main ingredients. One is to optimize the layout to minimize the longest check distance, and the other is to optimize the gate design to enable long-range interactions with high fidelity without requiring very strong Rydberg interactions. And how do we minimize the check distances? Well, the first step is embedding the torus in lower dimension. And this turns out to be a technique that's well known in the computer science world, which says that if you dilate your grid, you can map a torus with periodic boundary conditions onto a 2D grid that has next nearest neighbor interaction. So if I had periodic boundary conditions on a torus, if I think about this square grid, I would want 1 to talk to 8, 1 to talk to 57, 57 to talk to 64, and so on, and also these guys and these guys to be able to be connected. If I dilate the grid and then fold it along a vertical and horizontal axis, and then reinsert these quadrants into that dilated grid, everything that was every connection between edges in the toroid folded out to a surface becomes a nearest neighbor connection, and what was a nearest neighbor connection becomes the next nearest neighbor connection. So one can map the toroidal boundary conditions onto nearest neighbor connections, playing this trick, and nearest neighbor onto next nearest neighbor, and longer range intermediate connections will also become intermediate length connections after doing this. So we perform this dilation or renumbering of the qubits, and then we optimize the check qubit positions to reduce the maximal distance. I'm not going to go into all the details, but the end result is that the check qubits now have more than 2 long distance connections, but importantly, the longest range connections compared to the IBM layout and the Chicago layout are now reduced by more than a factor of 3. And this makes it possible with design of the Rydberg gates for longer range to do all the connections one needs in place without atom motion. And here's a little movie of that, assuming that we use different Rydberg levels with different interaction ranges for different connections. And this movie will go on for a while. And with the assumption of fast optical beam scanning, this provides a way of implementing this more rapidly than basing it on atom transport. Of course, to actually use that, we need to be able to make measurements in place. So we want mid-circuit measurements. And these atom arrays, mid-circuit measurements, have the challenge that the scattered light we use to make a qubit measurement will also be seen by other neighboring atoms, and that would give errors on data qubits. And so crosstalk-free measurements are a critical capability for measurement-based error correction, for efficient state preparation, and for entanglement distillation based on measurements. And so there was a whole bunch of work last year in this community looking at different ways of implementing these mid-circuit measurements. It can be based on transport. We're going to move the atom we want to measure far away, perhaps putting it into an optical cavity such that the scattered light does not impact data qubits. We might use 2 species. or we might use internal state shelving to make the atoms that we don't want to see the measurement light dark to that light. That's been done in the alkaline earth atoms by a few groups, and it's been done with alkali atoms in my group with cesium by mapping the qubit states, so 4,0 and 3,0 in cesium, taking advantage of matrix elements and microwave control to map those qubit states onto atoms sitting in these states down here. It can be dark to reading out ancilla atoms that are left in these upper states, and details are in this paper. I'm sorry, I'm going to accelerate here just to show some last things I want to talk about in the remaining time. So there's different ways of doing this. Transport is relatively slow. These shelving operations are complex. I'm excited about this two species approach, which does require more lasers to handle the two species, but has the potential to be very fast and straightforward. And so we've been working to implement a two-species system. And if I, for example, take rubidium and cesium, then I can have independent optical control of those two species. These are the wavelengths I need for different operations for cesium atoms. The red arrows are the wavelengths for rubidium atoms, and so there's good wavelength separation. And there's also good separation for the microwave control because of the different clock frequencies for these two types of atoms, 6.8 versus 9.2 gigahertz. So we've proposed to trap these two species in an interleaved array, which would provide for crosstalk-free mid-circuit measurements and error correction. And one can have strong interactions between different atomic elements by choosing appropriate atomic Rydberg levels for the two species, which can give very strong interactions due to resonant cases that occur by choosing the right levels. So, for example, this combination, rubidium 84, cesium 89, can give more than 50 megahertz at 10 micron separation. So here's some data showing co-trapping of rubidium and cesium atoms in an optical dipole trap. We can independently measure those atoms, and we can independently perform gate operations on them. For 2-qubit gate operations, we want arrays, and here we've developed a optical component that allows us to trap cesium and rubidium atoms in different spatial locations using a single wavelength of trapping light. And the idea is to use an optical mask that creates bright tweezer traps, and at the same time using different locations in the mask which have low transmission instead of high transmission. We can create blue detuned bottle traps, and so we use a trap wavelength that is to the red of the rubidium transitions and to the blue of the cesium transitions, and that allows us, with one laser wavelength and one component, to create interleaved tweezer and bottle traps. So we've fabricated such a component in the group of my colleague Mikhail Katz here in Madison, and we've implemented this actually at Inflection. And here's some data showing interleaved trapping of cesium and rubidium atoms in one setup. And indeed, already gates between rubidium and cesium atoms were just recently demonstrated by the Burning group using their setup in Chicago. And so we see that as a very interesting way forwards towards doing fast mid-circuit measurements and implementing these kinds of ideas. I'm a little bit over the hour. Can I take another 5 minutes here for just a few more slides?
Yeah, I think it's fine.
Okay. So, looking towards the future, there's a lot of activity in developing remote entanglement for atomic quantum networks. Here's a graph from a recent review paper that sort of documents some of the progress in terms of entanglement link efficiency for different distances. All these experiments are still relatively slow, but are being actively developed. And here in the Midwest, with support from some of the national quantum centers, we're really very excited about working towards implementing a Midwest quantum network. There's already a link between Argonne Lab and Chicago, and a number of people in the region here have plans to extend the network up to Madison and down to Urbana in the coming years. So these are things we're working on. But let me just close here by talking about not long distance entanglement, but using entanglement enabled via photonics locally to scale up logical processors. If you look at a circuit for quantum computation, you need global connectivity. Here's the quantum phase estimation circuit. Classically, we achieve connectivity with wires. In quantum processors, it's not so simple. And an outstanding challenge is how do we provide connectivity at large scale and with high speed across some logical processor? And, supposing we have a 3x3 block of logical qubits, patches of the surface code, the standard paradigm is chains of swap gates. We might think about long-range interactions, although Rydberg interactions will not scale to a long enough range to do this on a 100-qubit logical processor. We can think about physical motion of qubits, originally introduced in the context of trapped ions. Continuum's been doing this beautifully. Neutral atoms are doing this. Tends to be a little bit slow. We can also think about photonic interconnects. And in my lab, we've been developing a demonstrator of two-node photonic interconnects. So we have a cold atom setup here, a cold atom setup here, connected by optical fiber with a Bell state analyzer in the middle. By exciting a rubidium atom to a F equals 0 state, it can decay with a sigma plus or sigma minus photon, which leads to entanglement between the photon polarization and the Zeeman state of the atom. So that's atom-photon entanglement. We've built these nodes with a lot of in-vacuum optics that are fiber coupled, so working towards plug and play. And we now have single atoms in both of these devices. We're extracting single photons and not quite there, but actively working towards atom-photon and then atom-atom entanglement in this system. And one can think about using that to connect logical qubits in a processor. There's plenty of interesting optical integration challenges for how you do this at scale with multiple connections to optical fibers and optical switch networks. That's an interesting challenge that's not been fully solved. And I'd say it's not entirely clear today what's the best route to scaling up. Do we want chains of swap gates, long-range interactions, physical motion, photonic interconnects? I believe it's going to be a combination of these ideas that will push us towards scaling up neutral atom logical processors. And I'll just end with a final slide. And looking back at some of the progress I shared, there's been tremendous progress in the scaling of the number of qubits. At the same time, there's been great progress in improving the fidelity of entanglement in these systems. And I think these two charts show that the outlook for neutral atoms is bright. And I'm really excited about what the next couple of years brings for this field. So that's what I had. And thank you for listening, and happy to take some more questions.
Thanks so much, Mark. That was super interesting. We're a little bit over time, so I'll keep my questions short here. I guess I have some questions related to just like fundamental limitations of these devices. One is this problem of reloading. Would you consider that more of a technical or fundamental limitation? And then maybe just like naturally falling from that, ultimately, what do you think is going to be the most difficult challenge to overcome? Is it scaling of qubit number, entanglement fidelity, reloading, or gates, or something else?
Reloading is fundamentally a technical challenge, but I actually see incorporating active reloading during a circuit operation in a way that enables the circuit operation to proceed it is really our highest technical challenge. I'm very confident that we continue to push the entanglement fidelity to higher performance, and I'd say the physics limits set by atomic structure are beyond 5 nines. So this is all technical here, and I think we can do that the reloading at scale, when we're talking about tens of thousands or even hundreds of thousands of atoms, is a kind of an engineering headache. There have been a couple demonstrations already at the 1,000 qubit scale of continuously reloading atoms. And I do think that the two species approach, for example, provides some new knobs to turn that will make that reloading easier. But it's a pretty steep engineering challenge to really do that with high performance at scale. So that's a big challenge. And then I'll just say that some of the technologies that we need to scale up these systems, and in particular the optical beam steering technologies, the fast camera technology for rapid detection, they don't exist. Solid state approaches leverage the electronics industry, which has had trillions of dollars of investment and super high performance. We're not there yet with the kind of optics that we need and lasers. And I think that that's one of the challenges, is to develop those technologies.
Great, thank you. And then my final question related to drift, like noise drift in these systems, compared to the shot rate, especially. What is that? Like, how often, for example, do you need to recalibrate to maintain that 99.6% 2-qubit fidelity?
Yeah, so a lot of our effort has been in developing automated calibration and tuning systems. I'd say as long as we're able to maintain the lab environment well, and these processors sit in temperature stabilized boxes now, we're able to maintain performance for sort of a week kind of scale. And but the shot rate is currently relatively low. It's sort of 10 hertz is our current shot rate. So that's slow compared to some other modalities. And that's part of our effort, is to keep pushing that shot rate up. And there's room to improve, absolutely.
Yeah, great. Well, thank you so much for coming in, Mark. And of course, a big thanks to the entire audience for tuning in. If you'd like to continue this conversation, head over to the Qiskit Slack workspace. So finally, like this video, subscribe to this channel, and we'll see you next week. Thanks again.
Thank you.